Okay, so let's look at kinematics as an overview. So kinematics is basically just the study of the motion of objects without worrying about why they're moving that way. And firstly and foremost, we need to talk about scalars and vectors. Remember, a scalar by definition is a measurement that has magnitude only. A vector is a measurement that has magnitude and direction. It can't not have direction. You must have both. By definition, scalar is just the number, it's just the magnitude. The vector needs magnitude and direction. We've covered examples of scalars and vectors. There are many examples, but the ones that are most relevant to your kinematics are distance, which is simply the total length of the route traveled, including all direction changes and so forth, and speed, which is distance over time, or if you like, rate of change of distance. There are plenty of other scalars as well, like mass and time, which also come into play for you. And there are plenty of others, but these are the key ones we're going to be focusing on. And for vectors, we've talked about displacement, which is the straight line distance from where you're starting from to where you are now, including direction, because it's a vector. There is velocity, which is change in displacement over change in time. In other words, it's the rate of change of displacement. There is acceleration, which is the rate of change of velocity. So it's change in velocity over change in time. And basically any measurement that you can think of that includes direction is going to be a vector. Given that you've done dynamics already, you know that force is, is directional. So force is a vector. And therefore, so is weight, because by definition, weight is a force, but mass is not. And all sorts of things like, momentum as well, for example, is also a vector. Okay. So we also recognize that once you know the difference between those, vectors need magnitude and direction. But this direction must be given in all circumstances for a vector. Now, if you've got a one-dimensional vector, in other words, you've only got left or right, or you've got an up or down situation. So for example, if your particle is moving left or right, then by convention, we say to the right is positive and to the left is negative, although that's completely up to you. And by convention, if it's an up or down only situation, so if we throw something up and it comes down and it doesn't move left or right, then by convention, we say up is positive, down is negative. And these are situations where the polarity, in other words, positive or negative, of the vector represents the direction of the vector. So if I'm in a left-right situation and I work out that my velocity is +5, then it's 5 meters to the right. If it's -3, then it's 3 meters to the left. If it's an up-down situation and I have a acceleration of +5, then it's 5 meters per second up. If I've got a displacement that is -7, then it's 7 meters down.
Okay. Yeah.
But vectors, of course, might not just be 1D, it could be 2D vectors. And so the direction must be represented by an angle. Okay. And often, depends on the situation, often we might either use the angle versus the horizontal, or depending on the way the question is presented, we might do it as a true north bearing.
Mm-hmm.
But that's essentially the idea. You need some sort of angle, no matter what angle you're talking about, but you need some sort of angle to give an idea of the two-dimensional vector, because the vector could be, you know, in any direction in the 2D plane, on any left, right, or up, down, together.
Yeah.
So the idea of a 2D vector, and we revised this before, basically a 2D vector can be thought of as made up of two 1D vectors. So it's the sum of two 1D vectors. So if you've got a 2D vector like this, and it's got a length of, let's say, k at an angle of theta. So if it's theta horizontal and vertical, often we will consider this as the x, which is the horizontal component. And we could often term this y, which is the vertical component. And of course, we must know the angle. So we now have a 2D vector, and that means we want to work out its horizontal and vertical components. Simply use trigonometry to do so. And hopefully you can see that because it's a right angle triangle, this will equal k cosine theta, and y must equal k sine theta.
Mm-hmm.
Now we can actually also do the reverse. So similarly, two 1D vectors will add to form a 2D vector. Use trigonometry again to find the magnitude and direction. So hypothetically, if I had x going across and y going up, it depends on the situation, but imagine this sort of situation. So if I start with this, then what I'm trying to find is my red one. Start with the green and the red, green and the blue, and find the red. So we know x, we know y, and we want to find, you know, length, magnitude. Well, this is really easy. The magnitude m, magnitude, is just the right angle triangle, so you just use Pythagoras. And if you're trying to find the angle here, you would just again use trigonometry.
Mm-hmm.
And so basically for any two 1D vectors that you add together, you can then, at right angles to each other, you can just find the 2D vector by using trigonometry, Pythagoras for the magnitude, tan inverse for the angle.
Okay. Yeah.
In general, vector sums can be thought of graphically. So remember, a vector, if you're representing it graphically, is an arrow. So the length of the arrow is the magnitude. The direction of the arrow is also the direction of the vector. Now, if you're summing up vectors, then basically, you know, draw them sequentially, one after the other, from, you know, the start to the tip, and then, you know, then from the tip of previous to then draw the next vector. So for example, if this is A, if this is B, if this is, you know, C, then A plus B would be A, kind of like that, B, kind of like this, and so from start to end, this is the sum. Now, of course, I could also have something like, you know, C plus B plus A. So if I did 3 together, you're not limited to just 2. So C will look something along the lines of that. B will look something along the lines of this. And A will look something along the lines of that. So I've drawn C first. Then from the end of C, which is over here, I've then drawn B. And then from the end of B, the tip here, I've drawn A. Then from the very start, which is here, to the very end, which is here, we're going to draw this vector, and this vector will represent A plus B plus C. Make sense?
Yep.
Now, I'll get rid of this. Well, yeah, I'll get rid of it. I'll get rid of one. Well, no, we'll just do a new one. So you can also do differences. So note, the negative of a vector is the same length, but opposite direction. So if, for example, if that's A, then negative A would basically be like this. Same length, opposite direction. So that means to subtract a vector, simply add its negative. So basically that means if you've got something like B, so if you want B minus A, think of it as B plus negative A. So just draw B first. And then negative A looked something like that. And then as before, B plus negative A, or in other words, B minus A, would be that. Happy with that?
Yep.
Great.
Oh, actually, can we go through the related velocity? Yeah, that part.
Yep. So We'll do a bit more vectors before we do that then. So note that if you've got sort of points, so if you've got points A and B, then I guess, you know, the vector AB is basically, you know, from A to B, which, you know, is equal to the negative of BA, which is from B to A. So as I said, they're sort of the opposites. But another thing to recognize is if you've got some point O, which we think of as the origin, often we think of this vector here as, you know, A. From the origin to A is vector A. From the origin to B is vector B. Now note, AB is always B minus A. It's always final minus initial. And another way to think about it is AB, which we know is this vector from A to B. This is a vector AB, but this is B minus A. The shortcut is that, you know, AB is always the vector from B minus the vector at A. But if you're not so clear on why that is the case, we can kind of show you why it will be. So, you know, this is B, this is A. If I want B minus A, that means I want B plus negative A. So negative A is like this. So negative A would kind of look like this. Right? This is negative A. And if you like, this would therefore be B minus A. And you can see that, you know, this is the same vector, but in opposite direction. So it's the same length and parallel. Yep. And this is, you know, this is therefore going to be a parallelogram. And so therefore, those are the same length and in the same direction and parallel. So in other words, AB is always B minus A.
Mm-hmm. Okay.
Now, similarly, if you're applying to relative velocity, so for relative velocity, the idea is very simple. If the velocity of A is, you know, some number, so the velocity of A relative to the ground is, so velocity of A is A relative to, you know, the ground, like some sort of origin, right?
Mm-hmm.
So we'll normally just call this velocity of A. But velocity of BO is the velocity of B relative to the ground, which is like VB. Then the velocity of A relative to B from, so this is the velocity of A relative to B, so from P's perspective, is simply VA minus VB. You take away from who you're measuring. So you take the velocity of what you're measuring velocity of A, so it's velocity of A, and you take it away from the velocity of the thing you're measuring from, minus velocity of B.
Right, so always the one after of
A.
Yeah, I mean, like always the vector that after the of in the question would be the first one, right?
Yeah. Minus, you know, and you're always subtracting the relative to whatever.
Mm-hmm. Okay. Yeah.
Good. Makes sense?
Yep.
Okay. So the next thing we need to go through for kinematics is your, you know, equations. Mm-hmm. Often these are called, you know, SUVAT equations. Now we've derived them and all that kind of thing before, so we won't really use them here now. But basically, the SUVAT equations apply if acceleration is constant. We've mentioned before that your acceleration is just change in v over change in t. That's why it's v minus u over t. This can be also written as v equals u plus at. You have your s must equal ut plus half at squared, which you can derive as average velocity times time. And you've got v squared equals u squared plus 2as. Now, in all of these equations, v is final velocity in meters per second. U is initial velocity in meters per second. A is acceleration in meters per second. T is time in seconds, and S is displacement in meters. Pay attention to the units. You do have to actually pay attention to the units.
Okay. Yeah.
All right. Now,
Remind me, what's the unit of momentum?
well, it's just m times v, so it's just kilogram meters per second.
Kilogram meters per second.
But that's not really kinematics here. But yeah, it's kilogram meters per second.
I just forgot that one. Kind of.
Okay, sure. So these are your equations here. Now you also need to be clear with your graphs.
Mm-hmm.
So your graphs, I mean, with the equations, I don't think you have much trouble with them, so I didn't really go through it. But obviously, you know, you consider, you know, for example, if you've got v, u, and a, and you want to find t, then you use this equation. Like each equation has, you know, 4 things. So basically, if you know 3 out of those 4 things and you want to find the 4th, then pick that equation, basically.
Yeah.
Right. It's, you know, if you want to find t, you would never use this one because it doesn't have t, right? You're going to be looking for one of these 2. And depending on whether you've got v, u, and a, or s, u, and a, then, you know. And so picking which equation to use should be quite simple once you've read the question and determined what information you've got.
Yeah.
So graphs, you've got 3 main graphs: your ST graph, your VT graph, and your AT graph. Your ST graph obviously is a displacement time graph. Your VT graph is a velocity time graph, and your AT graph is an acceleration time graph. Now, we've said before that if acceleration time graph is constant, so think like your year 4 situation, that means if it's 0, that ends up meaning that you'll get a constant velocity and you'll get a linear displacement. So that hopefully lets you see that the gradient of an ST graph is the velocity, and the gradient of a VT graph is therefore acceleration. Now, the area under an acceleration curve will be the change in velocity, and the area under the VT curve is a change in displacement. Now, of course, the y value itself, you need to know, you just read off the axes, which I have yet to label. But the y value, of course, is representative of the name, right? So this is an ST graph, this is a VT graph, this is an AT graph. And T is always along the horizontal axis. All right, so that's the sort of relationship you've got there. And you can see that if you've got acceleration equals 0, then you'll get a constant velocity and you'll get a linear displacement. On the other hand, if acceleration is constant, that means you'll get some sort of linear velocity, and that means you'll get some sort of parabolic.
Okay.
So if A is a constant, then you get linear velocity, which then means you'll get a parabolic displacement. And in fact, if you think about it, we've said acceleration is constant for our SUVAT equations, but just think of what we said before, v equals u plus at.
Mm-hmm.
So you can see quite clearly that velocity is a linear function of t.
Mm-hmm.
Think of it as y equals mx plus b. This is your gradient, this is your x, and this is your b. And your s must equal ut plus half at squared. So you can also see quite clearly that algebraically, the displacement is an quadratic in t. Great. Well, that is basically everything you need to know for kinematics.
Okay.